Thank you. So this is a talk about a generalized logical framework. It's a joint work with Christian Sattler. So what is this about? We have this situation right now with two-level type theories and logical frameworks. And sadly, I'm not going to introduce them because I don't really have time for that. So I really hope that you already heard about these things. But in these systems, you can do metaprogramming over a single model of a single type theory. You have like a meta layer, you have an object layer, you have just one thing for object theory. And semantically, you choose a model of your object theory, but you do this choice outside of the system. And when you work inside of the framework, you can only see kind of a second order view of your model. So there are certain things which you cannot really talk about because you don't have any conception of context and substitutions of your object theory. And what we do here is we kind of generalize this to metaprogramming over any number of models of any number of type theories. And the models are also defined inside the system. And we can have both a first order and a second order view on each model. And we have a way of switching between these two views. And as a bonus, we don't use any substructural modalities. So there are some kind of prior art for kind of multi-theory frameworks, but usually they come with some kind of modalities. And if you're like me, you prefer purely structural type theories to kind of fiddling with variables and contexts and locks. So in this talk, we have a syntax of the generalized logical framework with some examples and increasing amount of syntactic sugar, and maybe a short overview of semantics, if you have time for that. Okay, let's just get to the basic rules of the framework. So we have a universe that supports ETT, let's call it U, and I have U has type U. As a simplification, I just use type in type everywhere. Okay, so and then I have base, which is a type. This is the type of base categories. So I'm already kind of giving a short semantic explanation for all of these things. So I have a type of base categories. I have one, which is the terminal category. And I have this PSH, and these are universes of presheaves. So as soon as you have a base category, you can have a presheaf of that thing. And then it also behaves as a universe, which supports all extensional type theory type formers. But then we have this restriction is that all elimination stays within the same universe. Okay, and then we have this cut, which is a type of categories in the presheaf of I. This is just a definition, so this is not part of kind of the axiomatic specification. We just define this to be using the type formers of ETT. And then we have this in, and this in and base. So this is kind of the weird part. So in is some kind of type of permissions for working inside presheaves over some base category. And we have some rule for kind of using the permission. And just for a kind of a very high level intuition, so the reason that we can avoid using modalities is that we use some kind of quantification trick over regions. So you have like parametric things in base categories, which then ensures that we are kind of not mixing up the different object theories and their different scopes in bad ways. Sorry? Implicit arguments. So implicitly quantified.
Maybe it's not a number.
So you mean, for example, this I? So it's like for all I implicitly,
Yeah,
and then. Yeah.
Yes, which. Oh, so it's the base. Oh, I see.
Yes.
The base.
Yes, it's a base. It's a base. Yeah. Okay. Okay, so basic things that we can do. Here a quick reminder of the rules. So presheaf 1 is a universe supporting extensional type theory. It's just a universe of sets, like presheafs over 1. And then working in sets, we can now define some category. And now, if we have this kind of permission token for working in presheafs over C, we get another universe, which is now presheaf base I, which is the universe of presheafs over C. And then we can kind of continue doing this, so we don't just get universe of presheaves over something, but also internal universes over internal presheaves, and so on and so on and so on, which might be useful for something, but I'm not yet sure. So, but at this point, we don't have any interesting interaction. So how do we interact between these different universes? And let's try to do some example for actually embedding some theory in this big logical framework. Let's try to embed pure lambda calculus into this big logical framework. So first thing that we have to specify, one thing that we have to specify, what is a second order model of some theory. So if we consider pure lambda calculus a second order model in some presheaf universe, is just a type together with abstraction and application, a beta rule, and an eta rule. It's fairly simple. And then I abbreviate this as S-bod I, as this type. And what is a first order model? I don't write it out here. It's a unitype category with families with lambda abstraction and application. So the point is that in the first order model, the substitutions and the context are fully explicit, while in the second order model, all you get is just a simple type with higher order operations. Okay, so then we have this rule that internally, to presheaves over a first order model, we have a second order model. And formally, so if you have some first order model and you have permission to work in presheaves over that thing, then we have a second order model in the appropriate presheaf universe. So, so this Sj is kind of, it marks the second order view that you get on for each of your first order models. So what this means is that each of these presheaf J universe, it works like a two-level type theory, because the extension ETT type formers you just get by default. And all the inner theory comes from this rule, which says that you can internalize something in the universe. And for example, so if I have any of this M, like any model of pure lambda calculus, then in this, I get this Sj. So I'm just referring to components of this Sj. And now I can write a kind of an inner lambda expression using this higher order notation. And if I add a bit more syntactic sugar, then it looks very much like an ordinary Hoas, which you would write in a logical framework. Okay. So more generally, we have this rule for every second order generalized algebraic theory. So we have all two-level type theories in GLF and all logical frameworks in GLF. So all two-level type theories are syntactic fragments of GLF. Okay, but this is not, so we don't really have, okay, so we can have like internal notation, but now we also want to move between first order things and second order things. And how do we move between these? We use the Yoneda embedding. So what does the Yoneda embedding say? If you have externally a context of lambda calculus, in presheaves, you just have a type. If you externally have a substitution, internally, you have just a function. And if you have a term, then internally, once again, you have a function. And then for these two things, so this in particular is just a statement of the usual Yoneda embedding. It's the full faithfulness of the Yoneda embedding. And now, so what we can do is we have this Yoneda as a family of operations. And we also have, sometimes we have this big lambda. I write big lambda. I had an idea to write an upside down Yoneda, but I thought that would be not very tasteful. So we have this big lambda for inverses of Yoneda. And now we can do some kind of notation for this. So let's just redefine some things. So for example, let's redefine the identity substitution using these two operations. So if you write this big lambda, inside the big lambda, you have to write some internal thing. And here I just write an identity function. And here inside the big lambda, I have to write an internal thing, which is a function composition. But then here I also have to move these external things into the internal world using the Yoneda. So So the J is kind of this permission token for working internally. But then the J is very easily inferable in a real implementation, I hope. So we can just drop it. So now it looks more like an ordinary function composition. And if you're a category theorist, probably you also drop the Yoneda, because that's something category theorists do. So, and then it just looks like an ordinary function composition. It actually starts looking like some kind of abuse of notation, right? But the nice thing about it that you can actually unabuse your notation and get something which is formally specified. And here, this is an example for some pattern matching notation. Like I'm just matching on a pair in this big lambda because I know that it's isomorphic to a pair. And then I define the weakening substitution. Okay, so how does it look for type theories? So for dependent type theories, like I want to have some type theories as object languages. So in the first order model, we have explicitly context, substitutions, types, terms, and so on and so on. So we have like, maybe we're using categories with families, and then we have some extra type formers and some extra rules on the top of that. But in a second order model, we only have just a type of types, and then a family for terms, and we have the usual higher order abstract syntax like specification for the thing. And we can also do, we can also specify this Yoneda embedding, and Yoneda embedding has an action on all sorts, essentially, of the theory. And so this works in, this Yoneda embedding can be specified in general. Okay, so let's look at a slightly more complicated example for abuse of notation. So here, there's a construction which is fully explicit, and it's I take it from this paper, and what's happening here is that I have some category with families. I have this F is some morphism going between them, and we are trying to do like a generic description of a logical predicate or so-called gluing construction. And then, for example, if you have a context gamma, then we want to interpret it in this logical predicate interpretation as a type over the F of gamma, like some kind of proof-relevant logical predicate. And then we can do this model construction, we can kind of continue doing it. But then the issue here is that everything is De Bruijn indices and explicit substitution combinators if we want to be rigorous. And you can already see here that I have to weaken. So P, if you know category with families, P is a weakening. I only have to weaken this A here, and then this one is just some mess. So, and then if we use this GLF notation, I didn't elaborate like this kind of sugar for context, but there is like a rigorous elaboration for this notation as well. I just don't present it. But basically, you can give names to things in contexts. And so you can see if you give names to things, it just starts looking like a very nice looking ordinary logical predicate construction. And moreover here, so here in the awful version, we just write a sigma type. And in the nice version, we write a big lambda, and we immediately pattern match on something up to isomorphism of sets. And once again, it looks like if you have an extended context, you just compute a logical predicate which says that something holds for the first projection and something holds for the second projection. So this is a lot of sugar, but the point is we can always rigorously desugar when in doubt. And I think this would be very nice for kind of syntactic translations and also some literature about compiling independently typed languages when there's plenty of notation which is either some kind of abuse or which is extremely hard if you want to be fully formal about it. Okay, so what is the semantics? So semantics, so each of these pre-Schiff I universes should be So each presheaf I should be a universe of internal presheafs over an internal category. So clearly, we have to do something with categories, but we have some issues with categories. So if we take this cut, which is the one category of categories, one problem is that there's no general pi. And another problem is that if you're only looking at presheafs, then we can form pi types of presheafs, and we can also form universes of presheafs, but they are not stable under substitution, essentially. And for this, And for this problem, we could try to do directed type theory, but it's a big complication. For this problem, we could try to use modalities, also a complication. But then here we can observe that we don't do any interesting categorical reasoning. So for this, this quantification trick is just purely for administrative purposes. We only want to ensure essentially this handling of internal and external languages. So, so we can do something more custom. We can say that the GLF contexts are some kind of trees of categories, where each node represents a presheaf universe, and each edge represents a shift between an internal and an external language. And so these are the contexts, and we also have to consider the parallel substitutions in the model. And so we have a notion of morphisms, which only have non-trivial action on the discrete data. So the morphisms preserve all the discrete data, but they, so the morphisms only have non-trivial action on discrete data, but all the non-discrete kind of real categorical stuff are just being strictly preserved. And this is how the stability is ensured for all the ETT type formers in this setup. So yeah, so this is the definition. So what is a tree of categories? I'm not sure how much time one more minute. Okay, yeah, it's a tree of categories. Let's look at some examples. So here on the left, you can see some kind of syntactic context, which I kind of extend in several steps. And on the right, you can see a tree of categories. So this is an illustration of how you compute context in the semantics. So the empty context is just an empty tree. Essentially, it's a single node. So this one is the terminal category, and it doesn't have any children. You can extend it with just an ordinary type, like the natural number, and then you add, you extend this category. Basically, you extend it with this as a discrete vibration. You take the total category of it. So this is some kind of discrete extension of your context. And then if you can add like a new in C, in which case you have to add the new branch and kind of a new mode, because now you also have to handle the internal language for this new essentially presheaf universe. And then if you can do basically you can add like a new mode into your context, which is a new node in your tree, or you can just add the ordinary type into your context, and then you take kind of an extension of some node with just a discrete vibration. Yeah. Okay, so some further work, but I don't have a lot of time. But what's important, so there's this advertisement. Please considering submitting to the TIDE 2025 workshop. So the deadline is June 22nd, and it's in Singapore, but you don't have to go there. You can do remote presentations, and you can also submit full papers or extended abstracts. So thank you.